Okay, looks like we're almost complete now with everyone coming in the room. Morning, everybody. Thank you for coming. My name's Rob Harrop, and I'm going to talk about microservices and performance of microservices. This is the second time I've given this talk. Last time I thought I'd seen the biggest room I could possibly give a talk in, but this room has beaten that. So very excited to be here. There's a gentleman in the front here who's got his feet up on the stage, looking very relaxed. Hopefully you won't fall asleep during this talk. It's quite a short talk. I'm not going to, it doesn't go on forever and ever. I don't have to rush like Josh did yesterday. I'm not going to speak at 1,000 miles an hour, I hope. And we're going to have some time for questions. We're going to have some time to maybe go off on a few tangents and just discuss performance in general. The motivation for this talk comes from my work. We do a lot of performance tuning and optimization. We talk to a lot of customers, a lot of companies, a lot of developers who are doing performance work. And I realized quite quickly that very few people have a very good framework for thinking about performance. They struggle to think about it in a structured way, in a constructive way. So I put this talk together to try to capture kind of the essence of how people should think about performance, how we can talk about it, how we can reason about it, and how we can do performance work in our jobs. And I like to think about the performance of microservices, and therefore the performance of distributed systems, as being the combined performance of the services that are collaborating and the links that they communicate over. And if you think about it, that makes perfect sense. You've got the bits of code that are running, they take time. And you've got the bytes and the bits that are flying between the services, they also take time to propagate. And you need to understand how all these pieces perform and how they operate to get a good grasp of the performance of your system. Is this going to work? So really, it's just about services and aggregations of services. And I think many people here will have probably done some rudimentary performance work with individual services. Maybe you've done some JMeter benchmarking, or you've used JUnit benchmarking, or something like that to test some code, or to test an HTTP endpoint. And that's kind of like a beginning step. It gets you sort of into the game, as it were, but it's not necessarily the right way of doing it, or the most sophisticated way of doing it, or even the correct way of doing it. And that gets to be more complicated when you start to think about, well, now I've got 3 services communicating, and there's a database, and there's a message queue, and there's all these things going on. So the aggregations of services is also important. Some of you may know me from the past. I was once co-founder of SpringSource and Spring Framework contributor, book writer, prolific at one-time speaker. This is the first year in many years that I've done talks again. More recently, I've been CTO of Skipjack, which we do machine learning for performance optimization. We have an office here in Krakow. One of my colleagues is in the audience, so if you heckle me, he will report it back to the team, and I will never hear the end of it, so feel free. I'm on Twitter, I'm on GitHub, but more importantly, I have a blog over at GitHub.io, and there are some relatively deep mathematical topics for performance. I obviously can't go into them in great detail in a 50-minute talk, but they are covered in much more detail on my blog, so you can kind of figure out, if you're interested, you can dive into the detail there. Today we're going to talk about 5 things. How to measure performance correctly. More specifically, actually, what to measure and what kind of quantities you're looking for, not specifically taking the measurements with some measuring tool. If you don't do that properly, then obviously everything else is kind of pointless. We're going to talk then about finding potential performance problems. In your system, how can you identify where are the big weak points? Where might you end up with some of the worst performance? Where might you end up with some of the best performance? Trying to figure out what are the hot spots. Likewise, trying to figure out what are the best candidates for optimizing my software. If I've got 10 services and I want to do some speed up, which service should I focus on? That's an interesting question. We tend to see when we're talking to customers who've got microservices that they maybe it's the product owner of one service you're talking to, and he wants to optimize his service, or you talk to the CIO who wants to optimize the most complex service they have. And there's no actual thought put into, in real terms, what's the benefit I might get? What's the speed up? Very interested in modeling performance. Performance testing and kind of benchmarking and so forth is quite an expensive process, both in terms of time and in terms of like CPU and compute and resource. So if you can model your system, if you can gain some kind of approximation that's useful, then that's a worthwhile effort. So we'll talk a little bit about that. And then at the end, I want to talk about forecasting scalability, because this is an important topic for many people. We want to know, right now I'm doing 1,000 users every hour. If I were to do 1,500 users an hour, what would the profile of my performance look like? Would I be able to maintain my current latencies? Would I drop off? What would happen? I'm not going to talk about measuring the number of instructions it takes on the CPU to run a particular piece of Java code, or how to measure block I/O, or how to measure network I/O. It's an interesting topic, and there are other talks about that, but it's largely a solved problem. If you're very interested, you should read this book by Brendan Gregg called Systems Performance. Very good book. He's incredibly deep on this topic. Before we start everything, it's actually really important to establish that we all mean the same thing by when we say performance, because I've discovered this is not the case. Many customers mean one thing, many customers mean another thing, and then there's the whole spectrum in between of people who just mean about 10 different things. So let's establish a clear meaning. If my clicker will work. For me, performance is really, oh gosh, sorry about this. For me, performance is how fast can I do a thing, and how many things can I do every period? So we might think of this more formally as latency, so how fast, and throughput, how many. I can do 1,000 requests per minute with a 95th centile latency of 20 milliseconds, something like that. That's what we really mean when we talk about performance. What we don't mean is throughput on its own, and what we don't mean is latency on its own. The two go together, and we're going to see why that is. So throughput's really easy to understand. It's kind of the rate of processing. It's the X per Y, requests per second, or jobs per minute, or, I don't know, messages per second as well. Or even we started applying some of these techniques to our development lifecycle, so kind of tasks per day, maybe stories per week, those kind of things in a Kanban or a lean development cycle. Latency is usually the thing that developers are most interested in, and throughput's the thing that executives are most interested in. So latency is just the time taken to do a thing. And this is where a lot of the confusion starts to come into play. First of all, what is the thing that you're measuring? Is it time to the first byte delivered to the client? Is it time just to run the code that generates those bytes? Is it time until the last byte? Is it time until a screen is rendered in the browser? Unless you establish that when you're talking about this with your colleagues and with your stakeholders, you'll pretty quickly find that most people are talking about something different. It's very common for developers to think about latency in terms of service time. How long does my code take to execute? Users typically think about latency in terms of how long until I can do something useful, how long until the page renders, and then you've got all that stuff in between. So the moral of the story is, very early on when you're doing performance work and when you're discussing it with your colleagues, please define what you mean by latency. This is going absolutely crazy. I want to make one note at this point. The most useful of these is probably time to last byte if you're doing microservices, or really if you're doing kind of web stuff and you can't measure in the browser. Service time is largely useless because it ignores the network. Time to first byte is also pretty useless because it ignores a whole bunch of the network. And especially if you're doing kind of redirects or anything like that, really the only thing that counts is when does the client see the last byte, when's the whole response cycle finished. So measuring this information, measuring these latencies, and measuring this throughput is quite interesting. And we have observed, and not just we, everybody who does performance work has observed that this is where everything starts to go wrong. And I hate to I hate to demonize Josh, but he made the fallacy yesterday in his talk, and I was at the Spring Conference recently, and the same thing happened in quite a few of the talks. People refer to average latency. And as we'll see, average latency really is a fairly meaningless figure. It doesn't tell you a lot about how your system performs. So I've put together this crib sheet, how you should measure the typical kind of microservice workload. So if you think about this, most of us are doing REST. So it's going to be request, response, request, response, request, response. And what we're interested is recording those discrete events. That's kind of the raw data. So you can record each of those requests, time-stamped, with the observed latency and whether it was successful or an error. So the success and error rates are also important. I've seen many performance tests that report incredibly high throughput because the system was serving up an error page. So if you don't track error versus success, you're going to get weird results. For throughput, it's very useful to track minimum, maximum, and average, and over some kind of varying time window. If you're storing the raw data, you can kind of do these aggregations after the fact. So it's useful to know in 5 minutes sliding window, what's the average throughput? Over the day, what's the average throughput? That kind of thing. For latency, though, the average becomes less useful, because if you think about how latencies are distributed, and we'll see this in a second, it's not that nice bell curve. It's not even really the nice kind of exponential curve. You get these weird distributions, and that means that the mean or the median can be pretty much anywhere. And there can be these really long tails, and the long tails matter. And because of that, you need to start measuring much more towards the tail. So for latency, I like to measure minimum. A minimum is useful. Can anyone guess why the minimum latency is useful? So the minimum latency is really good for calibrating that you're measuring quickly, because if your minimum is 0, you're obviously not measuring correctly, because you can't have 0 latency. You would be defying the laws of physics. The maximum is incredibly useful, and if you only really kind of have one thing you can measure, the maximum is probably the best one to measure, because it tells you what's the worst possible case. If your maximum latency is 20 seconds, and you're trying to hit 20, 30 milliseconds, you're way outside. So the maximum is a good indicator of what kind of service your customers are seeing. And then you back off from there, maybe 95th, 99th, 99.9th, those kind of percentiles in the tail that tell you useful things about how your system's performing. So I kind of alluded to this already, but it's worthwhile reiterating it. Latency is not exponentially distributed. It's not normally distributed. It's messy. You've got these heavy-tailed, multimodal distributions. And we'll see an example. I've got some graphs in a minute. The one thing to realize, and we're going to go through the maths of this, is that customers will see tail latencies far more frequently than you would imagine. The percentiles can trick you, because you think, oh, it's the 99th percentile, so hardly anyone will see latencies worse than that. Well, that's a trick. It's not true. Nearly everybody in a high-volume system will see latencies worse than the 99th percentile, and we'll see why that is. It's important to understand what latency means for your business. If you're doing high-frequency trading, latency is probably everything. If you're doing e-commerce, latency matters a lot. There's plenty of research that shows that adding on time to render on web pages reduces conversion, which is obviously lost money. So this is a typical kind of latency distribution. You can kind of ignore the numbers, except to note this is log scale at the bottom. So this is like 2,000 over here, this is 1 here, and this is 10 here. So you see there's like a big block of very quick requests, and then there's a little bump here, and then it kind of tails off. And there are requests like way out into 1,600, 1,700, 1,800 milliseconds here. This is fairly typical of a latency distribution. These are things that are being served from cache, or kind of they're all in the CPU cache, or they're all in some kind of mem cache or something. This is your typical service time when you're not cached, and then you have these really slow, maybe network blocking or something. So that's what a typical latency graph looks like. It's not very nice. So if we start to think about those tail latencies now, and this is important for microservices because you're typically going to make a lot of calls in a microservice system. If you think about it, you've gone from having all that code in one big lump that could quite happily talk to each other all the time and not worry too much about network effects and all that kind of stuff. And now you're changing those calls to go across the network. And no matter how well you architect your system to make that less chatty, there's going to be some chatter. And therefore, the tail latencies start to play in. We can calculate whether or not a customer is getting good service by this little formula. So I want to know, for example, whether or not a customer is getting something worse than the 95th. Let's assume that 95th is the good percentile. And they're going to make some number of requests. This may well be service A talking to service B, or it might be me, Rob Harrop, going to Amazon.com, or any number of interactions between services. So what does this mean in reality? Well, 42 requests. If a user makes 42 requests, they're going to see something worse than the 95th percentile about 88% of the time. Sorry, or rather, 88% of customers are going to see something worse than the 95th percentile. And that's the confusion there. I even made it myself when I was explaining it. The 95th percentile tells you kind of like, in isolation, how does each request look? But people are making multiple requests. So we're interested in knowing what's the probability of seeing something worse than that in all the requests I'm making. So if service A has to make 42 calls to service B to do some work, there's a chance, about 88% chance, he'll see something worse than 95th percentile latency. Where does 42 come from? It's not just from the Hitchhiker's Guide to the Galaxy. There was a Google study that shows the average number of requests made for a web page is 42. So when you include kind of style sheets and images and every tracker that tracks everything you're doing, Facebook, Twitter, Google, all those things, it's kind of 42 requests is the average, which is fantastic that it's 42. So it's very common for people to see these tail latencies. In fact, in an e-commerce site, most people will see some kind of tail latency pretty much all the time. In a microservices site, especially a kind of a high volume one, you should expect to see tail latencies quite frequently. So it makes a lot of sense to optimize your system to reduce that tail, to bring that distribution in tighter. And we can see a small simulation of this, like what it looks like if it all stacks up. So I'm very interested in this little slider thing. I hope you can all see it. So here, I've got the 95th percentile. What's the chance of seeing something worse than 95th percentile? If I make one request, it's obviously 5%, right? But if I start to add a few requests, if I maybe go up to 10, 9 in this case, then it's 37%. And the more requests I add, the worse that gets. So if we get to 42, we see around 88%. As we get higher and higher, so the more requests, the more time the customer interacts with your system, the more chance they're going to see something bad. And even as you push this percentile out, maybe let's get it up to like 99th, it doesn't take many requests to get to be more than average times they're going to see something worse than that percentile. 93 requests, so that's what? 2.5-page requests to Amazon.com. So in 2.5-page requests to Amazon.com, I'm going to see something worse than their 95th percentile. So you can't ignore your tail latency. You can't ignore your maximum latency. People are going to see that quite frequently. So another thing that we see when we talk to customers, and another thing that I think many of us have probably been guilty of in the past. In fact, I vividly remember having a conversation with Rod Johnson, who was the originator of Spring, where we made this exact same logical fallacy in our own minds. And it's talking about throughput and latency in isolation. And typically how this manifests is somebody will say, I can do 1,000 requests per second. which tells you very little, actually, about the quality of service that system is giving you. It doesn't tell you how fast those requests are being served in particular. It's very easy to get high throughput if you're prepared to trade off latency, because you can just queue up the requests and then just complete them all, but you're not necessarily worrying about service time. And I'm always reminded of this little comic strip. Who's seen Star Wars? More of you have seen Star Wars than that. I don't believe that. Either that or maybe Star Wars isn't a thing here. So there's a scene in Star Wars where Han Solo says that he did the Kessel Run in the Millennium Falcon in 12 parsecs. And this comic, in the first panel, it's the guy boasting. In the second panel, it's a little droid reminding him that a parsec is a unit of distance, not of speed. And in the end, the Han Solo character says, "I told you no facts while I'm bragging." And this is basically what I think about whenever a customer says to me, "I don't need to be optimized. I can do 100 requests per second, or I can do 1,000 requests per second." Because there's no sense of what that means for their latency, or what that even means for their customer. And we find that latencies and throughput are kind of intrinsically linked. Has anyone heard of Little's Law? Okay. I would have been dismayed if more of you had heard of Little's Law than had seen Star Wars. But thankfully, it was about 10 of you. So Little's Law is this great result from queuing theory, like back, I guess, maybe 1967, that tells us how to relate latency and throughput and utilization of a system into one simple way of thinking. And I'm going to, there we go. And it tells us this, that the mean occupancy of a system, of a queue, so that's the kind of the mean number of people waiting to be served and being served, is equal to the latency times the throughput. And what this means, if you kind of work this through, is that latency kind of drops off a cliff as throughput increases, or as the number of people in the system increases. So up on the y-axis here is latency, and along on the x-axis here is utilization. And this is 75% utilization. So you can kind of see between 75% and 0, so the system completely unloaded and the system 3/4 loaded, latencies are quite small. The moment we go past this, and particularly when we start to get past kind of 90%, we get this completely degenerate behavior, where all of a sudden, the overhead of queuing in the system vastly outweighs the actual service time taken. And we've all seen this in our real systems. You know, we've maybe got some locking, and there are tons of threads waiting on the locks, and all of a sudden the system just grinds to a halt. And no matter what we do, we can't get any faster. And it's a result of the kind of queuing up behind that lock. We had a system for a customer where they had written a custom log4j appender, and this appender made a very expensive database call, and the appender was also holding a lock, so the lock was held for an incredibly long amount of time, like 500 milliseconds. So obviously all these threads were queuing up, waiting for this lock, and couldn't proceed, and the system just had this awful kind of degenerate behavior where at around about 80% utilization, it would just fall off a cliff, and latencies would suffer really badly. This is why it's no use to talk about throughput without latency. Very high throughput means very high utilization, which probably means very, very high latency as well, so very bad latencies for your users. You need to think about these things in tandem. So when we're doing optimizations for our customers, we have to kind of bring them on this journey of saying, okay, we know you want to do 100 requests a second, or we know you want to do 500 requests a second, but what kind of service quality do you want to give to your users? If you're a microservice team, like what are your consumers expecting? If you're a web team, what are your end users, your kind of browser users expecting? And it's that kind of really governs where you're tuning to. If you're trying to hit 20 milliseconds for your 99th percentile, that's a lot different than trying to hit 20 seconds. There's a lot more leeway in 20 seconds. And this gives us a really interesting thing to watch for, to spot kind of performance problems in our system. High utilization is a very good early warning sign of performance problems. So if you're thinking about configuring some kind of alerting in your system or trying to figure out, how can I preempt some degradation in my performance, then high utilization is a good sign. So maybe if you're using AWS, you can set up like a CPU alert that says, if this instance goes over 70% utilization for 5 minutes, please send me an alert, or database CPU, or whatever. But watching the utilization of your systems, especially the long-term trend, if you start to see blocks, longer and longer blocks of high utilization, you're going to see longer and longer blocks of bad latencies. And for microservices, this is important because latencies stack up. And if this is just kind of common sense, right? You've got maybe a database at one end. You've got maybe your user interface at the front, and then you've kind of got all of these services in between. And the end latency is the sum of all those latencies. They stack together. And your customer's kind of seeing this combined latency distribution. And this is probably the most important performance point we'll see when moving from a monolith to a microservice. Because with a monolith, we don't have the network overhead, we don't have the communication overhead, but all of a sudden, by making these services stand alone and making them communicate over the network, we're introducing extra latency. There are tons of ways of simulating this, modeling this. There are some analytical models you can do with maths if you're interested, but simulation's typically the easiest approach. There's a really good tool called PDQ by Neil Gunther, if you're an R or a Perl coder, which can set up these very complicated Q theory models and then run some simulations on them and tell you kind of what you should expect. But if you want something really, really quick and dirty, there's this great tool called Guesstimate. I'm going to show you in a demo. And it's like in-browser Monte Carlo simulations. It's very cool. I'll show you how it works. So let's kind of quickly start with just some kind of analytical stacking. So this is a very simple kind of queue model using queuing theory. And I've got 4 services. So I've got a UI service, a logbook service, a leaderboard service, and a Cassandra service. And then at the end, I've put what the total combined latency is. And I can increase the utilization on each of these services in my sliders here, and we'll see how that impacts the latency. So the leaderboard's maybe going to be like 30%, the logbook, so same, UI, that's JavaScript, so let's say like 60%. Cassandra is supposedly very fast, so that's going to keep that quite small. And at this point, nothing's too bad. It's a fairly simple graph. There's no degenerate behavior. But let's assume that the logbook starts to really perform badly, or we're hammering it massively. So increase the latencies a little bit. It's not too bad around 70%. Not too bad past 80%. But if we go over 90, all of a sudden we get these kind of huge leaps. And this is because the latencies are increasing really badly as the utilization increases. And we can very quickly push that off to scale. This model is very, very basic. The issue with it is simply that it's modeling a very simple queue. It doesn't have any kind of uncertainty. So let's see if we can do this model with Guesstimate. And this is where I assume now that the internet for demos will work. And I think I'm going to be let down by that. This is annoying. Josh used the internet for his entire demo yesterday, and it worked perfectly. The moment I want to go online, it doesn't work. Well, let's leave that loading in the background, and hopefully it will come online. And we'll quickly switch back, and we can do it later. Who's read Release It by Michael Nygaard? If you haven't read this, you should. It's a really good book. It's all about how to build very high-quality, releasable software. And there's a chapter, or there's a discussion in there about this issue of SLA inversion. And really, it's just trying to capture something that's very commonsensical, but we don't necessarily think about all the time. Every service that's downstream of another service has to be faster. It has to be, has to be more capable. It has to be able to take the load of the upstream service and some more. So if you think about it, like your edge services, your UI services are going to be the least hit in terms of utilization. And then everything that's downstream of that is progressively more utilized. And there's this issue of SLA inversion where all of a sudden this service gets overloaded, and it causes all the services back up the chain to get overloaded as well. And this is why this kind of modeling is very, very useful. You can figure out, okay, what's the impact of this service degrading in performance? What's the impact if I have a slight issue with this service, which causes this service to get slower, then therefore this kind of unrelated service gets slower. And we'll go back to the demo with Guesstimate in a second, and you'll see how these kind of graphs all connect together. Who's heard of Amdahl's law? Okay, good. So we're probably all familiar with Amdahl's law when we talk about processors. It's this idea that maybe Moore's law has kind of been superseded by Amdahl's law now because we're going to more and more cores. Cores are not necessarily getting any faster. So there's this kind of limitation on parallelization. But we can answer a really important question for our microservice systems with Amdahl's law as well. In particular, we can answer, how much improvement can I get from an optimization? Or flip that on its head, where is best to focus on for an optimization? This is Amdahl's law. It's not too complicated. So it tells you the theoretical improvement in latency given a fixed workload. So the kind of big S latency is the theoretical maximum speed up. Small s is the speed up of the part you're optimizing, and this is kind of what it's equal to. And P is the percentage of execution time spent in the part under optimization. This is way more interesting if we take the limit. So we're figuring out what's the limit at max. If we were to get maximum speed up on the part we're optimizing, what's the maximum overall speed up? And it shouldn't come as too much of a surprise that it's proportionate to the amount of time you spend in the system that you're optimizing. So if you've got 4 microservices and you spend 10% of time in one and 20% of time in another, the theoretical speed up of optimizing the one with 20% time is bigger than the one with 10% time. And I have a diagram to show you that. So here I've got the same system I showed you before on that little simulation. 20% of time in the UI, 10% of time in the logbook, 30% of time in the leaderboard, 40% of time in Cassandra. If we apply Amdahl's law, we can figure out what the relative speed up is. So I get 1.67 times, so 167%, 111%, 125%, 143%. So this tells us it's not really worth optimizing the logbook because we can't get a lot of improvement. It does tell us it's probably worthwhile spending some time optimizing Cassandra, maybe some more disks, more memory. There's a ton of stuff we could do there. So you kind of flip this on its head. You're using this for decision-making process. It tells us that we should be driving our optimization choices based on our service utilization. So if we're spending a ton of time in one service, that's where you optimize first. It's very hard to optimize a whole graph of microservices at the same time. It's much easier to pull that graph apart and optimize piece by piece by piece. So if you know which one's the most heavily utilized, that's the one you should be focusing on. Who's heard of the universal scalability law? I think that is actually no one. Maybe some people. It's very bright up here. So the universal scalability law is work by Neil Gunther, who I mentioned before. And it tells us basically how a system scales and how we can predict how it scales. And it's a very useful law. We can do some very useful things with it. In particular, we can say, if I were to go from 4 servers to 8 servers, what's the speed up I should expect? If I was to go from 1,000 users at the moment to 2,000 concurrent users, what's the speed up I can expect? We can figure these things out. And there are some very interesting parts to the USL. In particular, there's an interesting question. Can increasing capacity reduce performance? So if I go from 16 servers to 32 servers, or if I go from 8 cores to 10 cores, can the performance go down? And the answer is yes. And actually, this is something we see quite frequently with our optimizations. So we'll be doing a single machine optimization. We might do 1 CPU, 2 CPUs, 4 CPUs, 6, 8, 10. And it's not uncommon to see 6 and 8 be round about the same and 10 be much worse. Typically, that's because of memory bandwidth issues. Like, there's only so many bytes you can shift over the memory bus. And we can predict this, and we can model this with the universal scalability law. Now, this potentially looks a bit confusing, but it's really not. So Cn is the relative capacity given n CPUs or n users. So n is the number of users, or it's the number of CPUs. Alpha is the contention overhead. So this is the overhead of just kind of queuing for things. And beta is the crosstalk overhead. And it's the crosstalk overhead, which you'll notice is quadratic in n, that gives you the degradation. It's the need to basically have everybody coordinate. And because everyone's talking to everybody else, that's where the degradation starts to happen. The more of those you add, the worse that gets. So imagine this in the logbook service I was talking about before. Maybe these are Cassandra nodes trying to reach quorum, or maybe they're cores trying to reach some kind of agreement about memory cache or something. But they're all talking to each other. It's a completely connected graph. And because of that, the more of these we add, the more connection paths increase, and we get this degradation in performance. I think it happens in the real world. So this is probably the most important thing. You do see it for real. And we can visualize this, and the visualization is kind of scary. When I first put this together, I wasn't quite convinced that I had it right. But it is right, unfortunately. So this graph here shows n. Let's say this is the number of cores in this example, and y, which is the relative capacity, so the relative throughput. If I increase the alpha factor a little bit, then what we see is that we degrade from linear scalability, which is the red line, and we tend now towards some maximum. And the more we increase that, the more that flattens out. And actually, basically, alpha limits your maximum throughput you can have. I'm going to scale this back because this happens really quite quickly. If we had a very small amount of crosstalk overhead, then all of a sudden you just get this huge degradation in performance. So this should tell you any kind of crosstalk is just dangerous in a system. It's where things get limited. It's where your system starts to limit. And you can see crosstalk on a single machine, and you can see crosstalk on many machines. So it's kind of instinctive to us all, I think, to consider maybe 10 machines trying to reach quorum about some data, and we can assume, I guess all instinctively, that that is overhead. It happens on a single machine as well, though. In particular, if you've got NUMA, which most multi-core, multi-socket machines will have now, and you're trying to have the CPUs reach agreement about caches, then they're talking to each other, and the more CPUs and sockets you add, the worse that gets. So it's not just a thing for microservices, it's a thing for the services themselves. Switch back to my presentation. So you should be measuring crosstalk, and you should be targeting it for optimization. Optimizing it can be quite hard. It's not so hard to think about doing it across machine, actually. Like if you're using Cassandra, and maybe you're saying, well, I want every possible machine I've got to agree on this write, one tuning thing is to relax that and say, well, maybe only 3 machines need to agree on a write, or some small number. Doing it on a single machine is a lot harder. And this basically reaches the question that most of our customers kind of in extension, when they've optimized their systems and when they're comfortable their systems are kind of performing as well as they can given configuration and so forth, the most interesting question then is, am I better off with more smaller servers or fewer bigger servers? And it's actually not that simple a question, because if you have more servers, you have more crosstalk between the servers. But if you have bigger servers, you have more crosstalk between the sockets. So you have to very carefully measure what that beta factor is. Where perhaps it's best to use the beta is to analyze and predict. So there's this really good ebook called practical scalability analysis with the Universal Scalability Law. It's like 29 pages. If you're interested in maths, it's very good. There's a lot of maths in there. But it gives you some insight into how you can predict things with the Universal Scalability Law. And I want to show you an example of that right now. Stolen, I will say, pretty much from the book. Where's my R? So this is R, for those of you who haven't used R before. It's just a statistical kind of data science language. Get rid of those. So I have some data. This is the raw data. And the first column here, if you can see that okay, is the number of kind of concurrent users. And this is the throughput, transactions per second. And this was taken, I believe, from a Cisco switch. And what I've done is subsetted that data. So I've taken just 8 samples from there rather than the full 32 samples. And what I want to try and do now is predict as close as we can to the original data from the sample data. So I've plotted the sample data, and it looks pretty good. It looks like we're about to reach some plateau, but there's no degradation in performance there. And what we can do if you're using R, and I'm not going to dwell on this for too long, we can use regression. So this is complicated and rather obtuse-looking code here, is doing nonlinear regression on the Universal Scalability Law function against the data set that we have. And it's going to try and fit and figure out what alpha and what beta is. Then we can plot that and figure out what the scalability will look like. So let's do that. I've got some plots here. I'm going to run this piece. And in this plot here, what you can see is, excuse me, this is a new laptop for me. I've just switched from Mac to Linux, which was brave because it took me a while to get the projector working. It's all good. Although this monitor down here, where I'm supposed to see what I'm doing, is not good at all. It's like cut off at the side. So the dots show the real data. So this is the original data frame that we saw. And the line shows the plotted, kind of the solved data. So you can see it tracks pretty closely, but then because there was no data out close to 32 users, there was only 20, it doesn't fit so well. But actually, it's not a bad approximation. It's lowballed it. There's nothing wrong with that. If we had more data, we could draw a better conclusion. But this is a very useful thing to do. And you can pretty much do this from your access logs. So if you've got some stable periods of time where you had 1 user, 2 users, 5 users, you can do it very easily. If you haven't got stable periods of time, there's some discussions in Neil's book about how you can do it. But it's very easy to take your data and predict what your scalability will be like if you added more machines. This is the book I'm talking about. It's called Guerrilla Capacity Planning. It's a strange book. I never thought I'd enjoy a book about capacity planning. But actually, it's pretty good. It's only about 250 pages. And Neil's thesis is all these grand, very expensive, like multi-million-dollar capacity planning initiatives are basically pointless. He favors a very light touch, very agile planning approach. And he discusses this in great detail in this book. It's very worthwhile reading if you're interested in trying to predict how your system will perform. Before we do the summary, let's see if we can get back to here. Why am I cursed? No, it's absolutely everything is out. I will put the link on my Twitter to my model. You can play with it. It's quite fantastic. Unfortunately, I just can't get it offline, which is very annoying. So, to summarize, performance is hard. And if you don't have a model for thinking about it, it's even harder because you'll make really bad choices. The most important thing you can start with is good quality measurements, because garbage in, garbage out. And that's actually quite hard, as we saw. Don't be trapped in this idea of just tracking average latencies. Don't also do what I've seen many performance management tools do, which is they start to average up percentiles of latencies. The average of a percentile is basically a meaningless value. So you need to think hard about the mathematics behind this. Monitoring utilization as an early warning signal is one of the easiest and most useful things you can do in a production system. It will very, very quickly predict where your likely problems are going to be in the future. It's no use just kind of slapdash adding new capacity or doing some performance tuning. You need to know where to focus. If you're interested in trying to improve user experience, then it makes a lot of sense to monitor per user latencies, not just per request. You know, how many users, how many customers are really seeing bad latencies, as opposed to just how many requests are bad latencies? And then kind of correspondingly, you want to select your optimization targets quite carefully. Amdahl's law is super simple. It's like do it in a calculator, do it with paper. You should apply this. Gather some data about your system, say, okay, well, this service is the most utilized. Let's do some tuning there. And then measure your crosstalk. Monitor your kind of throughput at different user levels or throughput at different core levels, and use this to forecast your scalability. If you can't do this in production, you can do this in a lab. If you can't do it in a lab, come and talk to me, because that's what we can do in a lab. And you need to think ahead for your performance. You need to make sure that you're not going to be surprised one day when your user level ticks up past the critical point of beta, and then you start seeing this really bad performance, and it just gets worse and worse. And I want to just quickly put this slide up. This is the reading list, so if you were interested just in the books that I just showed, and you want to photograph this one, please do. Release It by Michael Nygaard, great book. It's kind of old now, but everything still applies. Systems performance and Guerrilla capacity planning are kind of the Bibles that we use when we're trying to figure out, just basic performance, low-level stuff. Very, very good. And very quick introduction is the Practical Scalability Analysis ebook. You can read that on the train or on the plane home. It's very, very simple. And because we started 3 minutes late, and that was perfectly timed, we now have a few minutes for questions. I can't see, actually, if anyone's got their hand up. Are there any questions at all? No? Oh, perfect. Well, thank you very much, then.